We have the presenter for the next seminar on screen as well. So please make sure to join the next seminar in case it is relevant, particularly to your research area. Today, I am privileged to introduce you Dr. Tomaso Poggio. He's the Eugene McDermott Professor in the Department of Brain and Cognitive Sciences at MIT and the Director of the NSF Center for Brain, Minds, and Machines at MIT. He is the recipient of the 2014 Swartz Prize for Theoretical Computers and Computational Neuroscience and the IEEE 2017 Azriel Rosenfeld Lifetime Achievement Award. With that being said, I leave the stage for Professor Poggio.
Thank you, Mohammad. Let me start my talk on describing a framework for a theory of learning that could explain in particular deep networks and why they work as well as they do. Most of the buzz so far in machine learning in the last 10 years or so came from applications, not really theory. As an example, I showed two success stories in recent years have been in machine learning have been DeepMind, started by Demis Hassabis, and Mobileye, started by Amnon Shashua in Jerusalem. So DeepMind kind of developed systems that are essentially better than humans in the virtual world of games. So they developed in particular AlphaZero that has beaten human champion at chess and Go. And they've been doing great work on scientific problems like the 3D structure of proteins from their sequence with a system called AlphaFold. And Amnon has started Mobileye several years ago. Mobileye is a leading technology developer in the area of autonomous driving with systems based on vision and LiDAR. In fact, it's interesting to open here a small parenthesis about why machine learning is becoming so important, not only for engineering, but also for applications and business. This was a system that we developed together with Daimler, so Mercedes. And this was one of the very first system based on machine learning for doing recognition of pedestrian, detection of pedestrians. This brief video show was taken with a Mercedes where the system was installed in computers in the trunk. This was 25 years ago or so, more than 25 years ago. And as you can see, the detection is pretty good, but there are errors of false detection, like the traffic lights. Okay, at the time, 95, we were very happy with the fact that we got one error every 3 frames. At the time was a very good result. But that, of course, meant 10 errors per second. So that meant, from the application point of view, was hopeless. But now the same problem in Mobileye system has one error essentially every 100,000 kilometers of driving or so. And if you do a back of the envelope calculations, this is a million-fold improvements in accuracy during 25 years or so. So it's essentially doubling performance accuracy every year for 25 years plus. And that's why machine learning has become essentially a very ripe and good for applications. Okay, so applications are well ahead of theory, because at the same time it's still very interesting and somewhat ironic that we don't fully understand why deep networks like the ones used in many systems like Alexa or so are doing as well as they do. So the theory has been well behind the applications, but it's worth remembering the story of electricity. Electricity was discovered in 1800 by Alessandro Volta in Pavia, which is a small university town close to Milan, 30 kilometers from Milan. And it did that in a typical academical motivation. He wanted to show that Galvani was wrong, that you could have electricity from non-biological biological sources. And so he developed this pila, which is a pile of discs of copper, zinc, and wood. And it generates, the original one generates 2.1 volts for about 4 minutes. It was very important because it was the first time that a continuous source of electricity was available to researchers. And so having that, even without an understanding of electricity in 20 years after the discovery, researchers, inventors developed electrical engines, electrical generators, the whole electrochemistry, the telegraph was developed. Alessandro Volta himself had the design for it. It was made a count by Napoleon, just to give you an idea of the times. And the interesting thing, as I said, is that there were a lot of applications before an understanding, before a theory of electricity. It's only about 60 years later with Maxwell that a theory of electricity and electromagnetism was actually developed, and that opened the way to many more developments. You can count after Maxwell, telephone and radio, and television, and solid state electronics, and computers, and internet, and machine learning. So a lot happened. But for a time, for a few decades, without theory. We may be in a similar situation with deep learning. The discovery was also accidental in a sense, not guided by a theory like for electricity. But it's important to develop a theory, and there has been progress on this quite a bit in the last few years, and I'll describe what the situation is now. The general question is whether there are common principles among the several different architectures that have been developed that we see around and that do well in display some general form of intelligence. Until 4 or 5 years ago, convolutional networks, CNNs, were the main architecture. But in the meantime, there are transformers, and there are perceivers, and mixers, and other architecture. And there is, of course, the human brain. So the question is, what is in common? All of these perform pretty well on a number of tasks involving images and language. So question is, what are the theoretical principles that make all of this architecture work? By the way, please interrupt any time with question. I'll be happy to try to answer. Okay, so that's a question, what that principle are. And let me remind you quickly about, architectures, some of the architectures that have been used back 20 or 30 years ago. Shallow networks, basically one layer of parameters, had their main representative in so-called kernel machines, support vector machines, radial basis functions. These are networks that have one layer of units, one layer of coefficient weights, CI, and they can be written as in terms of a kernel, like a dot product between the input and each one of the stored examples, xi, and then learning is really finding the coefficient, the weights, ci, that are such that you minimize, for instance, the square loss with respect to the actual y output that you know for the training examples xi. More recently, deep networks have been used, in which you have several layers of units, several layers of weights. And what's happening in this network is actually quite simple. Unit is summating the inputs that arrive in the units, each one weighted by a coefficient, a parameter wij, and then this sum, a number, is passed through a nonlinearity, which is an RLU. So the value gets set to 0 if it's less than 0, and remain the same if it's positive. And in these networks, each unit behave in this way. And training the network means finding all the parameters, all the weights for each unit in every layer. The input could be an image, for instance, here. The output could be a label, like whether it's +1 or -1 in a binary classification task, or in a multi-class task, multi-label output. Finding the parameters is usually done with stochastic gradient descent. So you are updating the parameters in such a way that you are following the gradient. You are trying to minimize a loss function like the square loss or cross entropy, which means trying to get the network to output something as close as possible to the actual labels or y values for each of the examples, the one you know. And stochastic gradient descent is essentially, instead of using all of the example in each iteration, using a subset of the example chosen randomly at each iteration. All right. You can, of course, look at what you want to try to understand from different point of view. A useful way to look at how this network behave is in terms of 3 questions. One is, how representative are this architecture? How well they can approximate, represent an arbitrary input-output function, a function of many variables. Another question is, how can you learn the parameters? Do you have some result that tell you that you can always find a minimizer, a function, a network, a set of parameters that minimize the empirical loss, minimize your training loss? And related to it are questions that are, so this will be optimization, but related to this question that is really about learning is whether you have any result that tells you that the parameters you learn, the network you learn from the training set will do well on new data, so will generalize well. We had essentially answer to all these questions, this set of questions, in the case of shallow networks, in the case of kernel machines, but for general multi-layer networks, the answer is still not complete. Let me tell you what the state of this is. First of all, in terms of representational university, this is approximation, how well this architecture can approximate an arbitrary continuous function from an input domain of, say, 1,000-dimensional vectors. This would be like images in cipher that have roughly 1,000 pixels, to, say, an output that maybe have only 10 classes, 10 labels. Okay. You can this network represent any function from 1,000 to say 10 labels or not? And the answer is yes. They can represent as well as you want any continuous function on a compact domain, even if you have just one shallow layer. This was well known in already in the 80s. This is partly the reason why researchers in the 80s focus so much on shallow networks, because from the point of view of approximation theory, of representing any arbitrary function, you don't gain anything in terms of having multiple layers. However, what was not immediately noticed or emphasized was that that both shallow and deep networks, in principle, suffer from this so-called curse of dimensionality. And so the number of parameters that you may need to do this approximation depends exponentially on the dimensionality. In fact, number of parameters depend on the error you want to achieve, epsilon, measured, say, in the L infinity norm, and the dimensionality. M is the smoothness of the function. So if you can assume that the smoothness is very high, you can counter the fact that this number depends exponentially on the dimensionality. By the way, suppose M is equal 1, just for simplicity. If you have D equal 10 and you have a 10% error, you already have in the order of 10 to the 10 parameters, which is a lot. If D is 1,000, like in the case of cipher images, which are small, you have something like 10 to the 1,000, which is a big number. So this is a serious problem. Now, I will not bother you how this is proven, but it's basically showing that if you have a one-dimensional input and you have one layer nonlinear function like RLU or sigmoids, by linearly combining several of these sigmoids, you can approximate a polynomial in one variable, univariate polynomial, where the degree of the polynomial depends, it's essentially, 1 plus the number, sorry, then you can approximate well a polynomial of degree k with k plus 1 units, combining linearly k plus 1 units. And then you show that if you take dot product of a vector input with an appropriate numbers of weight vectors and combining again linearly these results, you can approximate multivariate polynomials in the variables. And then using connections between polynomials and Sobolev function, you can approximate functions so in a Sobolev space or with an appropriate degree of smoothness. But anyway, that's just a summary of the proof. But the interesting point is whether you can avoid this curse of dimensionality. And the result that I obtained a few years ago with Rushikesh, Maskar, and other collaborators is that if you have functions that are composition of functions with a bounded, each one with a bounded number of variables, then you can actually approximate a multivariate function, highly dimensional function, without the curse of dimensionality. Here is an example. Suppose you have a function that is a function of 8 variables. So the dot is a function, but is really the composition of several constituent functions, each one being a function of 2 variables. This is a binary tree where each node in the tree is a function of 2 variables. And you end up with a single output. And in this case, this is a binary, the graph of the function, the underlying function is a binary tree. In this case, if you have, this is your target function that describes the task. And if you have a multi-layer network with the same architecture, then you can show that instead of having a number of parameters that is in the order of epsilon to the minus d, you have a number of parameters that is d to the epsilon minus 2. So the key curves come from the constituent functions, each one having dimensionality 2. And so effectively, you can build, for instance, with a binary tree, a function that has as many variables as input as you want, but is made up of functions of 2 variables, many of them, so you need a deeper graph. And the complexity in terms of number of parameters will grow only linearly with d, with the dimensionality, not exponentially. And in fact, this binary tree is very simplified, but good model of a convolutional network. In fact, weight sharing would correspond to the case in which the functions in these layers, constituent functions, are all the same, and they're all the same in this layer. This would be weight sharing. It's interesting to note that in the proof of the theorem, weight sharing does not play a role. If you have weight sharing, your the number of parameters you need is even smaller because there will be shared parameters here and here. But what makes with what really avoids the curse of dimensionality is the locality of the constituent function, the fact that each of the constituent functions depends on a small number of variables. Okay. Any question up to this point? All right. Then and the proof of this result is actually quite simple. It's basically using this bound of the order of epsilon to the minus d over m and checking that the approximation you're doing at each stage for each of the constituent function does not explode as it propagates through the network. So I'll skip this proof unless somebody asks, and I'll just mention that the result does not just apply to binary trees, but applies to any function that can be described in terms of a function graph, which is compositionally sparse, which means it's a directed acyclic graph. That's a graph of the underlying function you're trying to learn. And but so basically the number of parameters you need is depends on the constituent function that has the maximum dimensionality of its inputs. So in this graph, for instance, would be probably 4, because there is one node that gets number of inputs, which is the node with the maximum number of inputs in this graph. Okay, so you can extend this to a general graph, and this, by the way, has the potentially interesting application that not only convolutional networks, CNN, enjoy this nice property of avoiding the curse of dimensionality, but potentially other non-convolutional graphs, underlying function that have a non-convolutional graph, as you may have, for instance, if you want to model the interaction between financial markets across the world, just as an example. Okay, just a few comments that, in the case of convolutional network, we essentially assume we know the structure of the underlying graph, because we assume that convolution describes well the translation invariance we want in images, and the locality comes from the fact that we don't need to look at the interaction between a pixel at the top left of the image and a pixel at the bottom right, say. So it's essentially assuming that images can be decomposed in objects, and objects in parts, and scenes into objects. So, and the same thing you can do for instance, language, in which you don't need to have just interaction between letters, but you can first look at the words, and then at sentences, and then at paragraphs, and then pieces of text composed of paragraphs. So you make this assumption, you find it works, and so you essentially know the graph of the function. In the case of convolutional network, you know which pixel interact with which other pixels in the first layer. This would be like saying, that it's just in this linear images would be like x1 with x2, x3 with x4. Maybe there will be interaction not shown here in the graph between x2 and x3 and so on. In convolutional network in images, typically instead of 2, the dimensionality of a constituent function is 3 by 3, it's 9. That's so-called kernel of convolutional networks. Okay, so it's interesting to notice in general this, the graph of a function. There can be multiple graphs, so there is not a unique decomposition. And so some may be better than others. But the intuition is here, for instance, an example different from the one I made before for the binary tree. Here would be real direct sparsity, in which the overall function is a function effectively of only 4 variables out of the 8, and it depends. It's the sum just of 2 functions. One depends on x1 and x2, and the other one depends on x3, x7, and the x8. So, so there are several ways of describing a function as compositionally sparse. The question is, are all functions compositionally sparse or not? And the first, when
Quick question.
Yeah.
Because, yeah, the question is, since it is, how far has theory caught up to the applications? Are there modern successful applications that use the theory?
Well, convolutional networks, I think, work because they are essentially binary trees that are compositionally sparse.
Mm-hmm.
So that's probably the key example. Dense networks, when you train them on a well, that's a separate question that involves a question about optimization. But dense network used, for instance, on CIFAR works much less well than convolutional networks, or the same is true for ImageNet. I'll tell you more about transformers later, but let me say that when we did the work with Hrusikesh Masker, I thought that his assumption of the underlying target function being compositionally sparse was a strong assumption. But in the meantime, it seems that this is not yet completely proved, but it's almost certainly correct. Let's take, for now, is a conjecture, is that if you consider functions that are efficiently computable, so it's either representable with a Boolean circuit that is implementable, or it's something that can be computed in a time that is smaller than the life of the universe, then this function must be compositionally sparse. And the argument, I give you a very simplified versions of it, but is that if you consider a function like the one we have for the CIFAR problem, which is much lower dimensionally than the one for ImageNet, just because the CIFAR has about, CIFAR images have 1,000 pixels, and ImageNet images are closer to 250,000 pixels or so. So a function with dimensionality 1,000, if you want to represent it as a table and assume you have a bit more than 3 bits per coordinate, so let's say 10 bins, this will correspond to storing 10 to the 1,000 numbers. Now, this is a real big number because 10 to the 80 is the number of protons in the universe. So 10 to the 1,000 is essentially impossible to store. So that's a kind of argument. There is a similar argument that is related to the proof of Kolmogorov and Arnold showing that Hilbert's conjecture about his 13 problem was wrong, but that's another story. Maybe I'll tell you if anybody is curious. But so this is really an assumption or a statement about properties of the world, of the function associated with tasks that we want to do in the world, like recognizing images or similar ones in terms of recognizing or completing sentences, like in language. So the key point is that we have to assume that the underlying function does not occur in the curse of dimensionality, because it can be represented as the composition of simpler tasks or simpler functions with a smaller number that depends on a smaller number of variables, much smaller. All right, now, all of this is kind of high level. We want also to say something about, we can find these parameters, assuming that the underlying target function is compositionally sparse. And here we're really looking at a deep networks, in this case with L layers, where you have a nonlinearity between the layers that acts here component-wise. The matrix, the weight matrix, each layer is W1, W2, and so on. And the input are in RD. And the analysis for now will assume that the W will, the network will represent in its architecture and the sparse compositionality. So for instance, the W here could be triplet matrices to respect, convolution at each layer. And we don't have a bias to simplify the theoretical analysis. And in terms of experiments, bias does not seem to matter. You can do achieve essentially the same results without biases. Consider binary classification. In application, usually one use batch normalization that normalize the activities at each layer, activities of the units in a certain complicated way, complicated in terms of modeling this theoretically. Instead of this, we normalize the norm of the weight matrices using a Lagrange multiplier and the loss function. And you assume overparameterization. So we have more parameters than data. So the loss function we have is the output of network G for each input xn. This is the examples. Yn is the label or the real value number associated we know for each example n. This is the Lagrange multiplier term, Frobenius norm 1 for each layer, plus irregularization terms in neural network called weight decay. And you can look at the gradient flow in this model with the derivative of, so this would be the change you are doing for each of the W matrices at each iteration, and the network we're looking at are shown in the left. Instead of the WL or W2 matrix, you have just a V1, V2, VL matrix, which is the same matrix but normalized, divided by its Frobenius norm. And then its Frobenius norm is called rho 1 or rho L. So it's completely equivalent. Completely equivalent because the RLU is homogeneous. So if you have a number inside the RLU, you can bring it outside. This is the RLU without biases. And because of the same homogeneous property, you can also consider this equivalent network where you have matrices that have norm 1, all of them, and then you have the output of the whole network multiplied by one number rho, which is the product of the rho 1 over rho L. And so you can minimize either the W1, WL, or equivalently the V1, rho 1, V2, rho 2, or equivalently the V1, V2, VL, rho. Okay. And if you do that, you have equation in rho, which is the product of the norms, gradient descent equation for those, gradient flow equation in the continuous case, and in the V. It's like changing coordinates from the W to the V and rho. And then let's leave that for a moment, and let's look at what we expect in terms of the minima of this function. So we square loss in our case. The square loss was not usually used until a year ago or so, and the cross entropy loss was used, but it was recently shown, and the same story played in the same way for radial basis function and kernel machines 10 years, 20 years ago or so. The fact that it does not matter whether you use hinge loss or cross entropy loss or square loss, you get results that are very similar, even when your classification, your problem is not regression, but binary classification, which is a little bit surprising. So the square loss is much easier than cross entropy to deal with theoretically. And in the square loss case, there are a topological theorem that basically says because of overparameterization, the global minimum that you can find is usually degenerate. So in other words, it's flat in many parameter weight dimensions. In fact, it's degenerate with a dimension which is W minus N, where W is the number of parameters and N is the number of training data. And usually you have much larger number of parameters than data. For instance, in CIFAR, typically you have networks that have 1 million parameters or more, and the number of training data is 50,000 for a 10 classes problem. So it's very degenerate, and you can expect to find zero loss. So to find solutions, minimize weights for the network that really fit the label. For instance, for binary classification, you interpolate the +1, -1 label. And there are many minimizers that interpolate because it's degenerate, the minima is degenerate. In fact, in our case, we expect that the loss function will be something like that. The origin is here, rho is radial, is essentially the product of the norms of the weight matrices. And at some point when rho is large enough, you can interpolate. This is zero level, zero loss. And then you have degenerate minima. This will be a two-dimensional parameter space. In effect, you are in a 1 million dimensional parameter space. So it's very flat in many dimensions. And all of this choice of parameters will interpolate the labels. The regularizer, that weight decay part of the loss function, will push you to the set of parameters that interpolate but have minimum rho, so minimum product of the norms. And in fact, it's what we find in experiments. Again, CIFAR, we find that rho grows until you look at interpolation, and loss, training loss goes essentially to zero, minus 0.2, so you do interpolation, and the test loss decreases, but it's larger than zero. Okay, There are several properties that you find. In the interest of time, I will skip this and just tell you that the everything works in this case, approximation and generalization, and in fact generalization, you can show that generalization will directly depend on rho. In other words, your error on the test set, your error on new data will depend on rho, and the smaller is rho, the better you are. So rho, which is the product of the norms, determines how well you are going to generalize. And in fact, we have demonstration that if you have worse test error, you have a larger rho. And in fact, we get, let me see, this, well, let's see, even this term 2 rho over square root of n, which is very close to a full bound, including the constant for the test error, is very close to be non-vacuous, so less than 1. The test error should be between 0 and 1 when you have 10,000 training data in CIFAR. And the behavior of the bound, which is here on the right, is very similar to what you observe when you measure the test error. So this is evidence saying that the rho, in fact, controls the test error. Okay, so the point here is also that you can get a good test error with a number of example, which is much less than the number of parameters. So overparameterization is not a problem. And let me finish, because of time, saying that the key part is this compositional sparsity that it looks like a statement about function you're trying to learn in the real world, that essentially, effectively, they're all compositionally sparse. If you know the graph of the sparse function, like in the case for convolutional network, you can optimize and find the value of the parameters, and value of parameters that do well in terms of test error, doing gradient descent and L2 minimization. If you don't know the underlying graph, then I did not have time to tell you this, but this will be the case of transformers. And here we are more, I'm in a conjecture stage in which the conjecture is that self-attention find a sparse representation of the input, similar to what you can do in compressed sensing with L0 or L1 minimization. I can give you more details if you ask me a question, but so in this case, you make the assumption that the underlying function is sparse. You don't assume, however, you know the underlying graph, and then you can find a representation which is sparse through the algorithm used by transformer and probably other ones. So let me stop here. Thank you, and ask you for questions. Thank you.
Thank you. Any questions? You can maybe just ask directly or type in the chat box. I have a question. So this motivation that deep learning or artificial neural networks are good because they are universal approximators might be shared by other models such as SVMs. And I think there's some a result with similar approximation theorem for SVMs. But what is this is shared, what is the difference or something particular to deep learning that you think has made it, or at least theoretically, makes it a better model compared to SVM or other alternatives?
What is SVM or ST?
A support vector machine.
Yeah. Well, the reason is that with a shallow network, you cannot exploit compositionally sparse structure of functions. So you cannot avoid the curse of dimensionality, even just at the approximation level.
Yeah, so even if we increase the size of the mid layer, still we are going to face
it. It will increase exponentially. So that's the problem.
Okay. Thanks. And then there's another question. What is your opinion on dimension-independent bounds such as barons?
You mean for a generalization error, I assume?
Probably. I'm not very familiar
with for generalization error, if you use VC Vapnik, VC bounds, VC dimension bounds, you get for, you get for cases like this, your bound, what in the table is 2 rho over square root of n. The numbers you get there will be more than 1 million instead of 1.3, because it's the number of parameters multiplied by the depth. So those dimension-dependent bounds are completely vacuous, and they always be in the over-parameterized case. They cannot be used. So this is also, one argument people used when they were wondering about over-parameterization, how can we get good generalization when we have more parameters than data? Well, the reason is that you can decrease the complexity of the function by working on the norm of the parameters rather than the number. And that was well known also in the margin theory, for instance, for support vector machines. It's the norm that matters.
Thank you. And then there's another question. Do you think this hypothesis will still work on quantum neural networks? Will they be able to get close to 10 to the 100?
Yeah, I don't know about, I've not thought enough about this, so I'm sorry, I cannot answer. Actually, I'll ask, I'm meeting in half an hour at Seth Lloyd, who has been working on quantum computation, so I'll ask him. Good question.
Okay. Thank you so much for your time. It was very interesting in my opinion, especially your discussion about chairs of dimensionality.
Very good.
Thanks. And there's this last question. So it's clear that over-parameterization does not contradict generalization. But if one were to compare two over-parameterized where one has more parameters, why does the larger model generalize better? Does this have any connection to sparsity?
Yeah, it's not always true that sparse models, if you increase over parameterization, you perform better. I think if you have over parameterization, it's and you know the sparse graph of the function like CNN network, then over parameterization make it easier to find the minimizers of the empirical loss, because these minimizers are very degenerate. They occupy a large space in phase space, in the space of parameters. And there are good arguments, formal arguments, why you should find them faster if you are over-parameterized. I don't think that over-parameterization per se improves generalization, but if you have a better control of the empirical error, that will help, of course, assuming that you can then minimize the norm of the, for instance, the rho in our terminology.
Thank you. Thank you, everyone, for attending this talk. We'll also release the recorded talk soon. Thank you, Dr. Poggio.
Thank you.
Okay.
Thanks.
Bye.